Before we begin, take a moment to get comfortable. Let your arms go heavy, your breath slow. And as you listen, feel free to leave a comment sharing what time it is, where you are, and what city or village you're listening from. It's love to know. And if you'd like more quiet stories like this one, don't forget to subscribe so they gently appear when you need them most. Now, what does it mean to float, to not fall, to exist in stillness, surrounded by nothing, no ground beneath, no wind above, only space, high above the Earth's surface, where air thins into silence, and silence thins into vacuum? A strange truth begins to reveal itself. Floating is not freedom from gravity, but rather a perfect dance within its pull. Gravity is not simply a force that drags things downward. It is the architecture of space itself. And to understand what floating means, we must begin not with motion, but with stillness. Let's begin on the Earth. When you stand still on solid ground, you feel your weight. The subtle resistance beneath your feet, the pressure of your bones against your muscles, all of it the result of gravity's constant pull, countered by the Earth's surface pushing upward. This resistance, this push and pull, is what we interpret as weight. But imagine, the floor disappears, not because gravity stops, but because you and the floor are now falling together. In that moment, if no air resists your movement, you float. This is why astronauts aboard the International Space Station appear to be weightless. Not because gravity is gone. In fact, the force of gravity at that altitude is still about 90% as strong as it is on Earth's surface, because the station and everything inside it is in free fall around the Earth, moving forward so fast that as it falls, the Earth's curve drops away beneath it. It never lands, because it keeps missing the ground. This is what an orbit is, perpetual falling, wrapped around a planet. Now, step beyond Earth's orbit. Imagine drifting further into space, beyond the gravity wells of moons and planets, into the quiet reaches where gravitational forces cancel and diminish. In such regions, there is no up, no down. Objects float, not because there is no gravity, but because they are balanced within many subtle gravitational pulls from distant stars and galaxies here. Motion continues unless disturbed. A gentle nudge can send an object drifting endlessly. But why does anything fall at all? To understand that, we must shift our understanding. For centuries, gravity was thought to be a force acting at a distance. Isaac Newton formalized it, a mathematical law that explained the motions of apples and planets alike. But in the 20th century, Albert Einstein reshaped this vision. In his general theory of relativity, Einstein described gravity not as a force, but as a curvature in the fabric of spacetime. Mass bends space, and objects move along the curves created by that bend. Picture a stretched fabric. Place a heavy ball in the center. The fabric sags. Now roll a smaller ball nearby. It spirals inward, following the curve, not because it is pulled, but because the space it travels through is no longer straight. Floating, then, is motion along the straightest possible path to a space that is no longer flat. This is how planets orbit stars, how moons orbit planets, and how a spaceship drifting without fuel will follow the gentle curves of warped spacetime. Not because it is being tugged, but because the space it moves through tells it where to go. In space, there is no true rest. Everything is falling. Everything is moving. Even when you seem still, you are caught in the motion of Earth, the motion of the sun, the motion of the galaxy. But stillness, relative to what? If two astronauts drift beside one another, and both are in free fall, they will appear to be still. Yet both are hurtling together through vast space. This illusion of stillness is not proof of no gravity, but a sign that gravity is acting equally on both. In Einstein's words, a person in free fall cannot detect their own falling because everything around them is falling equally. This is the equivalence principle, one of the quiet truths at the heart of modern physics. It is why a person floating in a falling elevator would feel weightless, why the experience inside a small spacecraft orbiting the moon feels similar to drifting through interstellar space. Floating in space is not escaping gravity. It is living inside its geometry. Now, let's consider the vacuum itself in the regions between stars and planets, where pressure drops to nearly nothing, K, and where a single atom may drift across kilometers before colliding with another. We enter what physicists call hard vacuum. It is not pure nothingness. Quantum fields still fluctuate. Radiation still travels, but for most purposes, it is emptiness. And in this emptiness, gravity is perhaps the only presence that cannot be removed. There is no air resistance, no friction, only the gentle warping of space-time's guiding motion. This is why satellite paths remain predictable, why galaxies swirl as they do, why light curves around black holes, forming gravitational lenses. In this vacuum, floating is a form of obedience to geometry. Let's go deeper. What does floating mean? Near a black hole, you approach the event horizon. Tidal forces grow your head and feet, feel different pulls. Space itself stretches, steepening the curvature. Floating becomes dangerous, but still, it is free fall, motion without resistance, a straight path through bent space. If you could survive and watch someone fall toward a black hole, their time would slow, not because they changed, but because gravity curves time itself. To float here is to float into time distortion. Gravity does not only shape where you go, it shapes when you go. A clock on a mountain ticks slightly faster than one at sea level because less gravity curves time less. This is not theory, it is measured. It is why GPS satellites must correct for relativistic time dilation. They float above Earth. But even that slight difference in gravity changes their clock. Floating, then, is not outside of gravity. It is inside its deepest expression. And so, we drift, not through void, through a universe sculpted by mass and motion. We float, not because we are free, but because we are guided. And gravity, silent, invisible, holds every orbit, every moon, every drifting atom in its unbroken embrace. Out in space, when you see an astronaut tumbling gently inside the cabin of a spacecraft, or a tiny bolt spinning quietly through the still, airless dark, it's easy to imagine that gravity has been shut off, like a light switch flicked to 0. But the reality is more subtle, more persistent. Gravity is not absent. It never is. It simply works differently when you're in free fall. We return to the International Space Station, roughly 400 kilometers above the Earth. The ISS completes an orbit every 90 minutes. Inside, astronauts sleep, eat, run experiments, exercise, and observe the planet there forever circling. And yet, every object not fastened down, every droplet of water, every tool, every limb floats. But not because gravity is gone. The station is in constant descent around the Earth. It falls, but always misses. This continual free fall is what we call microgravity. It's not true weightlessness. It's just the sensation of all things falling at once. If you were to toss a pencil across the cabin, it wouldn't fly in a straight line due to the absence of gravity. It would still be governed by gravity, just subtly so. If you waited long enough, even in that gentle vacuum, it would gradually drift toward the side of the cabin facing Earth. The tiniest difference in gravitational attraction, even at these altitudes, still exists. So, floating is always relative. Relative to what's falling, to what's accelerating, to what's resisting the pull. But let's leave Earth's orbit now. Let's drift outward, toward the edges of our solar system, beyond the reach of major planetary bodies, where only starlight and ancient dust remain. We begin to see, floating in its most profound form. Imagine the Voyager 1 spacecraft, launched in 1977. It has now passed beyond the heliopositive boundary, where the solar wind slows and interstellar space begins. Voyager floats in a place where the sun is little more than a bright star, where no planetary gravity dominates, and yet gravity is still present, because gravity never ends. The spacecraft is still moving along a path dictated by every body it's ever passed. The gravity of Jupiter once flung it faster, and the gravity of Saturn altered its course, and now it's coasting, floating, the deepest quiet our species has ever touched. There is no resistance in space. There is no wind to slow it. There's no air to drag it down, so its motion continues untouched. Unhurried, it is still falling. It's just on a time scale and path so wide, so slow, we no longer perceive it. This idea that everything is always falling feels counterintuitive, but it's a truth that shapes how we move through space. Even light falls. Einstein's general theory of relativity predicted that light should follow the curves of space bent by mass. This was confirmed in 1919 during a solar eclipse. Light from distant stars passing near the sun was observed to bend just slightly by the sun's gravity. Photons, massless particles, still respond to the warping of space. So if light can float and light can fall, what does this mean for gravity itself? It means gravity is not just a downward pull. It is a geometry, description of how space and time are shaped by presence. Wherever there is mass, there is curvature. Wherever there is energy, there is motion shaped by that curvature. Let's go smaller. Back on Earth, in laboratories that study atomic particles, floating takes on an entirely different meaning. In a vacuum chamber, atoms can be suspended with lasers. These atoms can be cooled to near absolute zero, so still that their behavior becomes governed almost entirely by quantum mechanics. Here, even the pull of Earth's gravity can be neutralized through precise control. Scientists can make atoms float for a few milliseconds long enough to study the pure physics of motion, acceleration, and inertia. In space, the same experiments can last far longer. That's why the Cold Atom Lab aboard the International Space Station was developed. It allows scientists to observe ultra-cold matter in microgravity, providing insight into how gravity interacts with quantum systems. So floating doesn't just help humans feel weightless. It helps us probe the fundamental structure of matter itself. Let's return to scale. Imagine a planet orbiting a star. Now, imagine that star is orbiting the center of its galaxy. And the galaxy, it, too, is in motion spiraling through the cosmic web, influenced by the dark matter that permeates the universe. Everything is floating in a medium we cannot see, and yet nothing is free. Every object, every atom, every planet is connected by gravity's thread. There's no true isolation. Even in the coldest void between galaxies, gravity extends, whispering, pulling, curving. This is why, when we look through telescopes at distant galaxies, we often see them distorted, bent. This bending, it's called gravitational lensing, occurs because massive clusters of galaxies warp space so powerfully that even the path of light is altered. Galaxies behind them appear stretched, duplicated, or smeared into arcs. It's a silent reminder. Gravity acts on all things, even across millions of light-years. So what does it mean to float in a universe like this? It means to move freely, but not alone. To be in harmony with the structure of the cosmos. To follow the curves set down by ancient collisions, by matter arranged long before we were born. It is not a denial of gravity, It is its fulfillment. In this sense, astronauts aboard the ISS are not resisting Earth's pull. They are yielding to it completely. the same way that moons yield to their planets, that comets yield to the sun, that stars yield to the black holes at the heart of galaxies. Floating is not escape. The key is acceptance. And as we send probes deeper, as we design missions to Mars, to Europa, to Titan, we are not trying to leave gravity behind. We are trying to navigate within it. Every spacecraft that launches must calculate the gravity of Earth, the Moon, the Sun, and the target world. Even when we slingshot past planets, we are not escaping their grasp. We are borrowing it, using their momentum tool to change our own path. Floating is a form of negotiation. Gravity speaks in curves, and motion is our reply. In deep space, far from stars, you would still float, but not aimlessly. Even the tiniest mass, like a speck of dust, would eventually be drawn to something. Somewhere, given enough time, it would fall toward structure, toward the nearest curve. Floating is not absence, it is balance. In the vast silence of space, the concept of up and down dissolves. On Earth, we are anchored, feet pressed to the soil, liquids settling in containers, breath rising gently. But out beyond the firm boundaries of atmosphere, direction becomes relative. There is no up, no down, only away, only toward. Only vectors governed by a quiet, persistent force that never stops shaping the cosmos. Gravity in school books. Gravity is often introduced as a force, an invisible rope, pulling all things downward. This classical view, rooted in Newtonian mechanics, is useful for everyday understanding. Drop an apple, it falls. Fire a cannonball, and its arc is a result of gravitational pull and initial momentum. These interactions are calculable, tangible, but in space, gravity behaves less like a rope and more like a landscape. Imagine placing a bowling ball in the center of a large, stretched sheet of rubber. The weight presses down, creating a dimple. Now, roll a marble along that sheet. If the marble approaches the dimple, it curves, not because the ball reaches out and pulls it, but because the sheet itself is curved. This was Einstein's gift, a new vision of gravity, not as a pulling force, but as the bending of space-time itself. Mass curves space, motion follows curves. That's all. Now visualize a star, not just resting in space, but pressing into it, bending it. Planets nearby are not tethered to the star by invisible strings, but rather sliding along the curved indentations created by the star's mass. When a planet floats in orbit, it is in fact falling inward, just fast enough to keep missing. This is true of the Earth around the Sun, the Moon around Earth, and artificial satellites like the ISS. But here's something more subtle. The astronaut on the space station is not in zero gravity. The gravitational pull from Earth at that altitude is still approximately 90% of the force felt on the surface. So why do astronauts float? 'Cause both they and the station are in continuous freefall. The spacecraft falls, because it also has enormous horizontal velocity. It keeps missing the Earth. It's like firing a cannonball so fast that the Earth curves away underneath it forever. This is why the term microgravity is more accurate than zero gravity. Now, extend this logic. What if you were floating in a point of space far from any planet or star, say in the lonely region between galaxies? There, gravity is weaker, but not absent, because the universe has mass everywhere, in dust, in dark matter, in radiation, and gravity, being long-range and cumulative, still operates even across billions of light years. Even at the edge of the known universe, you are still within a gravitational landscape, its features simply more gentle, more stretched, less familiar. Let us now consider what it means to float in that vacuum. Floating suggests stillness, In space, everything is always in motion. The Earth rotates at 1,600 kilometers per hour at the equator. It orbits the Sun at 107,000 kilometers per hour. The Sun itself drifts around the center of the Milky Way at 828,000 kilometers per hour. And the Milky Way, it hurtles toward the Andromeda Galaxy at over 2.1 million kilometers per hour. So even the quietest float is relative. A spacecraft drifting peacefully near Mars is still riding an enormous velocity through the galaxy, as are we all. And this introduces another idea: inertia. In the vacuum of space, there is no air resistance, no wind, no friction to slow you down. This is Newton's first law in its purest state. An object in motion stays in motion. If a satellite is launched and no forces act upon it, it will continue moving indefinitely, or until it's pulled into the orbit of another mass. This is why we can send probes like Voyager 1 and 2, New Horizons, and Pioneer 10 and 11 beyond the solar system. They coast silently through the gravitational contours of deep space, needing no engine. Only gravity and inertia guide them. Let's shift focus now to how gravity changes in different conditions. The surface gravity of Earth is about 9.81 meters per second squared. On the Moon, it's just 1.62 meters per second squared. This change affects not only falling objects, but also bodily experience. Astronauts who trained in lunar gravity simulations often found that balance and movement were surprisingly difficult. Not because of lightness, but because feedback from muscles and inner ears tuned to Earth's force in microgravity. Other phenomena arise. Fluids behave strangely, not flowing downward, but forming spheres due to surface tension. Muscles atrophy. Bones lose density. Even blood redistributes, causing faces to puff and legs too thin. The human body is designed for a gravitational load. Remove it, and the body responds, often in discomfort. And yet, microgravity offers insights impossible on Earth. In freefall, crystals grow more symmetrically. Biological processes can be observed without the interference of sedimentation, and in the study of fluid dynamics. Space laboratories allow researchers to isolate phenomena that gravity would overwhelm on Earth. But what about floating in the ultimate vacuum? The voids between galaxies. Here, gravity is minimal, a T, never zero. Particles drift for millions of years before encountering anything. A grain of interstellar dust released by a dying star may travel light years before its path is deflected. Yet, its journey is still shaped, perhaps faintly, by the tug of nearby galactic structures. This helps explain the behavior of cosmic filaments, thread-like structures that span hundreds of millions of light years. These filaments, composed of galaxies, gas, and dark matter, form a web-like scaffolding. Gravity binds this web, and even in the most desolate patches, motion is dictated by the gentle curves of spacetime. Now, let's go smaller again. Even individual photons, particles of light, are subject to gravity. While they have no mass, their energy and momentum mean they still follow spacetime's curves. This is why gravitational lensing occurs. A galaxy cluster bends light from objects behind it, making them appear distorted or duplicated. And in extreme environments, gravity does more. Near a black hole, space-time becomes so warped that escape becomes impossible. Not even light can float free. This is the event horizon, a one-way threshold. Beyond it, floating becomes collapse. Gravity overwhelms all resistance, but outside that boundary, near the edge, interesting things happen. Time slows down, appears to stretch. Light, climbing out of the gravitational well, loses energy, its frequency lowered, its color reddened. This is gravitational redshift proof that even photons experience floating as an effort. They are not exempt from the landscape. So what does floating teach us? It teaches patience. Whether it's a feather descending in a sealed chamber, satellite gliding through deep space, core, a photon stretching across the universe. Floating reveals the invisible structures beneath reality. It shows that gravity is not a barrier to overcome, but a texture to understand. Everything that floats is still connected, still moving, still shaped by the unseen threads that knit the cosmos together. And even when we build machines to escape Earth's grip, rockets, satellites, space elevators of the future, we are never truly beyond gravity. We are only learning to dance with it more elegantly in the final analysis. Space teaches us that floating is not about resisting gravity. It is about being in agreement with it, aligning with its curves, following its slow, soft invitations. Floating is gravity. If you're still awake with us, gently drifting through this quiet corner of the cosmos, feel free to subscribe for more calming science journeys. You can even share what time it is, where you are, and where you're listening from. We love hearing from minds all across Earth's orbit. Now, let's settle back into the void, in a world without air, without sound, without resistance. What does motion mean? Let's return to a small object, a metal bolt, let's say, drifting outside a space station. K. It was accidentally let go by an astronaut during a routine EVA extravehicular activity. K. A slight nudge, imperceptible at the time, sent it into motion. And now, in the vacuum of space, nothing will stop it. There is no friction, no wind, no water to slow its drift, no atmosphere to push against it. Only gravity, subtle, patient, may someday alter its course. Perhaps it will remain in orbit around the Earth for decades, perhaps centuries, or perhaps it will be tugged gently by the moon or perturbed by solar radiation pressure. Maybe a micrometeoroid will collide with it and send it spinning in a new direction. Or maybe, like so many tiny human-made objects, it will become part of the ever-growing cloud of orbital debris. The point is this: motion in a vacuum is pure. It is undisturbed, uncorrupted. It's beautiful in its continuity. This purity is what makes space such a profound laboratory for physics on Earth. Even the most controlled experiments are influenced by factors we can't eliminate: friction, weight, air currents, gravity itself. Okay? In space, however, we can isolate principles with astonishing clarity. Newton's laws, for instance, become not just approximations, but observable truths. When astronauts push off a surface inside the International Space Station, they don't slow down unless they hit something. They don't float because there's no gravity. They float because they and the station are falling together perfectly, endlessly around the Earth. This idea that free fall equals weightlessness is one of the most counterintuitive concepts in physics. It means that the sensation of weight is not a fundamental property, but a consequence of support. Here on Earth, we feel heavy because the ground pushes up on us. In free fall, that support vanishes. Okay? You are, for all intents and purposes, falling forever. Let's step back and look at the mathematical beauty behind this. Einstein's field equations describe how mass and energy curve spacetime and how that curvature dictates motion. These equations are complex, yes, but their essence is poetic. Matter tells space how to curve. Curved space tells matter how to move. In this view, floating is no longer mysterious. It is motion along a path defined by geometry. You are not suspended in defiance of gravity. You are gliding along the very lines it has drawn. Now, imagine a spacecraft deep in interstellar space, beyond the orbit of Pluto, beyond the Oort cloud. Out there, gravity is weak, but still present. The spacecraft is not being pulled exactly, but it is still responding to the shape of space. Every photon of sunlight that reaches it has taken a curved path. Every signal it sends back to Earth, even traveling at the speed of light, is influenced by the curvature of spacetime along its journey. This gentle influence is detectable. In 2015, the world watched as the LIGO observatories detected gravitational waves for the first time. These waves, predicted by Einstein a century earlier, were ripples in the very fabric of spacetime, caused by the collision of two black holes over 1 billion light-years away. The effect, stretch and squeeze of reality, smaller than a proton, but real, measurable, floating, distorted. This moment taught us something profound. Space is not just a backdrop, it is a participant. And in that realization, floating gains new depth. It is not just absence of contact, it is navigation through a living medium. Let us now consider gravity's role in shaping the earliest moments of the universe after the Big Bang. As the universe cooled, matter began to clump. These clumps became stars, galaxies, clusters. Why? Because gravity, weak but cumulative, pulled matter together. Floating particles, wandering in the dark, began to feel each other's presence. The first structures formed, and every atom in your body today is here because of that process. Without gravity, there is no floating. There is only drifting apart, endlessly, meaninglessly. Gravity gives structure. Floating reveals that structure. Even the cosmic microwave background, the faint afterglow of the Big Bang, shows the imprint of gravitational interaction. Tiny temperature fluctuations, just fractions of a degree, map the density variations that would later become galaxies. These slight differences in density meant slight differences in gravitational attraction. And those differences changed everything. We now turn our gaze toward astronauts aboard long-duration missions in microgravity. They experience not just floating, but biological change. Fluids shift upward, affecting vision. Bone density decreases. Muscle atrophy occurs without constant resistance. Even the heart changes shape, becoming more spherical, less efficient. To counter this, astronauts exercise for hours daily. They use resisted machines, harnesses, and cycles. These routines simulate the load their bodies would normally experience on Earth. But the body still knows. It still senses the absence of gravity's full touch. This presents challenges for missions to Mars, where long-term exposure to microgravity could impair strength and coordination during landing. Solutions being explored include artificial gravity, created by spinning sections of spacecraft to generate centrifugal force. It's not true gravity, but it mimics its effects. These efforts underscore gravity's role, not just in cosmic structure, but in human health. Floating, while poetic, is not without cost. Let's close today's quiet reflection by zooming in on a floating droplet of water inside a spacecraft, free of gravity's pull. It forms a perfect sphere, held together only by surface tension. A gentle touch from an astronaut's finger sends it wobbling, rippling, dancing. This is motion without interruption. It will not fall. It will not flow downward. It will only oscillate, slowly, gently, until the energy fades. This single droplet becomes a mirror of the universe, silent, suspended, obeying forces both known and subtle. Never at rest, yet never in haste, just floating. Floating is gravity, observed from within. As we continue this journey, let us now shift our focus to a more theoretical realm, one that holds the keys to many of space's deepest mysteries, the black hole. These celestial objects are not merely fascinating phenomena of science fiction, but real and unavoidable consequences of gravity's unyielding nature. A black hole is not a hole in space, but a region where space-time itself has become so curved by gravity that nothing, not even light, can escape its grasp. It is an area where mass is concentrated in such a small volume that the fabric of space-time bends infinitely, creating what we call a singularity. Now, what does this mean in terms of floating? We imagine ourselves near the event horizon of a black hole. We would find ourselves in a strange, unsettling state of freefall. Our orbit would slowly decay, spiraling inward as the immense gravity of the black hole dominated the surrounding space. As we approach the event horizon, the gravitational force would become so intense that our perception of time would begin to warp. From the perspective of an observer, watching from a distance, the astronaut falling toward the black hole would appear to slow down, stretching as time dilated near the event horizon. The closer they got, the slower they seemed to move. At the very moment they crossed the event horizon, however, they would no longer be visible. From their own perspective, they would experience no such delay. They would continue to fall inward, drawn toward the singularity, the point of infinite curvature, where the laws of physics as we know them break down. This curious phenomenon tells us much about the nature of gravity and its effects on both space and time. Floating near a black hole is not just a metaphorical exercise. It is a reminder that gravity, when extreme, warps the very structure of the universe. It demonstrates how profoundly the curvature of spacetime can change an observer's experience, bending their perception of time, distance, and even reality itself. But let us move away from the extreme, back to the more familiar reaches of space. When we observe the planets, moons, and asteroids that populate our solar system, we see the effects of gravity acting at a more manageable scale. Yet even here, floating is not merely about the absence of gravity. It's about the delicate balance of forces. Take, for example, the moon's orbit around the Earth. The moon, much like the ISS, is in a state of continuous freefall, falling toward the Earth, but due to its high velocity, it continually misses. The result is a stable orbit, a continuous, perpetual fall that keeps the moon in place. This orbital motion is a dance of balance of centrifugal force pushing outward, and gravity pulling inward, The faster the moon moves, the less gravity can pull it toward the Earth. Conversely, if the moon were to slow down, the gravitational attraction would increase and it would spiral inward. But this balance is delicate. Without the moon's orbital velocity, it would be pulled into the Earth. Without the Earth's gravity, the moon would drift off into space. This dance, which we call orbital mechanics, is the most common form of floating in space. It is the invisible, precise balancing of gravitational forces in motion, allowing planets, moons, and even spacecraft to travel through the vacuum of space without ever needing to land. In fact, this principle is what allows spacecraft to travel across the vast expanse of our solar system. When a probe is launched toward another planet, it does not simply accelerate toward its destination. Instead, it is carefully guided, using the gravitational pull of other planets to slingshot, gain velocity, and conserve fuel. This method, known as gravity assists, uses the gravity of planets like Jupiter to accelerate the spacecraft. Probe is not free-falling directly into the planet's gravitational field. It is carefully directed to use the planet's gravity to adjust its trajectory, slingshotting away and continuing on its path. Floating in this case means not only balancing gravitational forces, but also intelligently navigating them. It is about utilizing the environment of space and using its gravity as a tool to move through the cosmos. But there's more to this story. It's floating, even in the peaceful, near weightless world of space, is not without its challenges. Humans, in their unending desire to explore the stars, have encountered new and surprising effects of gravity in the form of space flight-induced physiological changes. When astronauts leave the comfort of Earth's gravity, they face a significant challenge: microgravity, which creates the sensation of weightlessness, causes many biological systems to function differently. The heart, which is accustomed to pumping blood downward with the help of gravity, suddenly has to work harder in space. As the body's fluids shift upward, astronauts experience a redistribution of bodily fluids, which can lead to facial puffiness and fluid retention in the upper body. The lack of gravity's pull on the lower extremities makes muscles and bones lose mass. This condition, known as muscle atrophy, occurs because muscles no longer have to work as hard to support the body. To combat this, astronauts must regularly exercise to stimulate their muscles and bones, ensuring that they maintain strength. They use treadmills, cycling machines, and resistance machines to simulate the effects of gravity and preserve their physical health. Without this countermeasure, long-term space travel could result in severe muscle weakness and bone loss. Space agencies like NASA and ESA, the European Space Agency, are particularly interested in this phenomenon because it has direct implications for future human missions to distant destinations, like Mars. Without gravity to help maintain their bodies, astronauts must actively work against the effects of microgravity, using exercise regimens and special equipment to stay healthy. What does this teach us about gravity? It teaches us that our biology, like everything else, is finely tuned to the environment it has evolved in. Gravity shapes not only how we move through space, but how our bodies function. In space, we're not just floating in a vacuum. We are floating in a different environment altogether, one that doesn't support our natural processes. And yet, with the right tools and adaptations, can survive and thrive in this altered state. But beyond the effects on the human body, space also reveals a more universal truth. Gravity is not just a force, it's a key element in shaping the entire structure of the universe. Every interaction, every orbit, every system that exists, from galaxies down to the smallest atoms, is influenced by gravity. From the cosmic scale of galaxy formation to the microscopic world of subatomic particles, gravity plays a fundamental role in the way things are arranged, the way matter behaves. Gravity is what causes stars to form from collapsing clouds of gas and dust, glues gas together, causing temperatures to rise and nuclear fusion to begin. It drives the evolution of stars, guiding them through their life cycles from formation to supernova to the creation of black holes. Gravity shapes the formation of planets, pulling gas and dust together to create the rocky and gaseous worlds we know. Again, in turn, the gravity of these planets influences the formation of moons, rings, and other cosmic structures. In the end, floating in a vacuum is more than just an absence of gravity. It is a different perspective on gravity itself. In space, we can observe its effects without being bound by them. We can see how it shapes the motion of planets, how it governs the life of stars, and how it keeps us anchored to Earth. But floating also reminds us that, in the grand scheme of the universe, gravity is both an enabler and a constant force of nature that keeps everything in motion. As the exploration of weightlessness continues, one begins to realize that space does not offer a true absence of gravity, but rather a vast expanse where gravity's presence is continuous, though often subtle, even at the farthest distances. From massive bodies, gravity never quite disappears. It merely becomes weaker, less commanding, and more background than foreground. This leads to a profound realization. There is no such thing as truly escaping gravity. There is only falling with it, floating in its grasp, or moving fast enough that its pull is balanced by one's momentum. In this way, space does not abolish gravity and veils its versatility. Consider the space between galaxies' vast regions, spanning millions of light years. Even here, gravitational forces are at play. These enormous distances are not empty, but threaded with invisible lines of gravitational influence. Galaxies tug gently on one another. Clusters of galaxies swirl around shared centers of mass. Entire superclusters drift ever so subtly through the cosmos, held together not by bonds of matter, but by the quiet persistence of gravity. And in this immense cosmic framework, the idea of floating becomes relative. A spacecraft far from any planet, suspended in deep space, may feel no pull in any direction, but it is still within a gravitational field, perhaps from a nearby star, or even from the entire Milky Way galaxy. It is simply that the gradient, the difference in gravitational pull between one side of the spacecraft and the other, is so small that it appears weightless. Now, turn attention back toward Earth, and think again about the International Space Station. It floats, yes, but not because Earth's gravity has stopped affecting it. In fact, the ISS is still within roughly 90% of Earth's surface gravity. What makes it appear weightless is its motion. It is constantly falling toward Earth, but its forward velocity ensures it keeps missing the ground. It loops around the planet in a state of continuous freefall, balance between gravity's inward pull and its own forward inertia. This is known as orbital freefall. A similar principle governs satellites, whether they're used for communication, weather tracking, or Earth observation. Their altitudes vary. Some are in low Earth orbit, like the ISS. Others are in geostationary orbit thousands of kilometers away, but they all rely on the same fundamental mechanics. Each is placed into a position where its speed matches the gravitational curvature of the planet, allowing it to circle indefinitely untethered, but not unbound. The concept of floating, then, is not an escape from gravity, it is a masterclass in gravitational harmony. To better understand this balance, one must examine the concept of gravitational potential energy. Every object in a gravitational field has energy by virtue of its position. The higher it is, whether above Earth or near a star, the more potential energy it possesses. When an object falls, this potential energy converts to kinetic energy, the energy of motion. When it moves away from a mass, kinetic energy is traded for potential energy. This exchange is how spacecraft leave Earth. Rockets launch with enough kinetic energy to overcome the gravitational potential. The higher they go, the slower they need to move to stay in orbit. Conversely, to descend or re-enter Earth's atmosphere, they reduce their velocity, lowering their orbit and converting some of their altitude-based potential energy back into motion, which is eventually absorbed by friction. One cannot discuss gravity in space without eventually encountering the Einsteinian perspective. While Newton described gravity as a force between masses, Einstein revealed a more nuanced picture. Gravity is not a force in the traditional sense, but a curvature of spacetime caused by mass and energy. According to Einstein's general theory of relativity, massive objects cause spacetime to bend around them like a bowling ball on a stretched rubber sheet. Other objects follow these curves, not because they are being pulled, but because the fabric of the universe is guiding their path. In this way, planets orbit stars not by being tugged on by invisible strings, but by moving along natural paths in curved spacetime. This reimagining of gravity helps explain phenomena that Newton's laws cannot, such as the precession of Mercury's orbit, the bending of starlight around massive bodies, and the gravitational time dilation observed near massive objects. It also deepens the idea of floating in curved spacetime. A freely falling object is not defying gravity, is actually following the most natural path possible, a geodesic, or the straightest line available in a curved space. This is why astronauts, when floating in orbit, are not experiencing a lack of gravity. They are in geodesic motion. They are following the straight line path carved into spacetime by Earth's mass. Their experience of weightlessness is the result of being on that path. Just as someone falling off a building experiences the same temporary sense of floating, despite being fully subject to gravity, Einstein's perspective also explains more exotic phenomena, such as gravitational waves. These are ripples in spacetime caused by the acceleration of massive objects like two black holes orbiting and merging. As they spiral together, they generate distortions in spacetime that travel outward at the speed of light. These waves were predicted a century ago, but only directly detected in 2015 by the LIGO Observatory. The detection of gravitational waves not only confirmed one of Einstein's final predictions, it also demonstrated that gravity is not static. It can move, it can vibrate, it can carry information across the cosmos. But what of floating in the absence of any massive object? What of the hypothetical spacecraft lost between galaxies, adrift in the most remote corner of the universe. Even there, gravity's fingerprints remain. Cosmic background radiation remnants from the Big Bang hums faintly in every direction. Quantum fluctuations still ripple through the vacuum. The spacecraft, though unanchored, is not without influence. Gravity may be faint, but it is eternal, and here lies a final revelation. Floating in a vacuum is not proof of gravity's weakness. It is evidence of gravity's subtlety. Gravity does not need to roar to be felt. It whispers, it nudges, sculpts galaxies and curves light and holds atoms in the embrace of stars for humanity. Space is the proving ground of this quiet strength. Each astronaut floating freely is participating in a cosmic ballet, choreographed not by sound or wind or ground, but by invisible lines of curvature. Each satellite in orbit is a student of Earth's shape. Each planet circling its sun is proof that gravity, unseen, remains the most influential artist in the universe. To float in space is not to be free of gravity, is to become part of its rhythm, to learn from it, see the universe not as a void, but as a symphony of motion, gently orchestrated by the geometry of mass and time, and in sleep. When thoughts drift and consciousness loosens its grip, there is something familiar in this sensation. The feeling of floating, of being weightless, untethered mirrors the dreamlike silence of drifting in the vacuum of space. Perhaps this is why stories of astronauts and space travel are so soothing. They remind us of vastness and calm, and the kind of silence that does not echo, but absorbs the float, is to let go. To follow the path that gravity draws, and to trust it. In the vacuum, there is no resistance, no noise, no urgency, only motion and stillness and the continuous unfolding of space and time. As we continue our journey through the delicate dance of gravity, we are reminded that while floating may seem like a simple state, it is, in reality, a profound lesson in the fundamental forces that shape the universe. The absence of resistance in space allows us to observe the true nature of gravity, not as a force acting from a distance, but as an ever-present, shaping influence on the very fabric of space and time. To understand floating more deeply, we must return to one of the most remarkable objects in our universe, the black hole. A black hole represents the ultimate manifestation of gravity, a place where the curvature of space-time becomes so intense that not even light can escape its grasp. At the event horizon, the point of no return gravity reaches its most extreme, warping time and space in ways that challenge our very understanding of physics in space. Where gravity is the dominant force, floating takes on a new meaning. It is not simply a state of weightlessness. It is a delicate balance between forces that shape everything around us. The curvature of space-time, caused by a massive object like a black hole, draws everything inward, bending the paths of photons, planets, and even light. This warping is so severe that once inside the event horizon, there is no escape. The pull of gravity is inescapable, and everything falls inexorably toward the singularity. But floating near a black hole is not an exercise in simple weightlessness. SID is an experience that changes our perception of time. As an object approaches the event horizon, time begins to slow down relative to an observer farther away. This phenomenon is known as gravitational time dilation. The closer an object gets to the black hole, the slower time seems to pass for it from the perspective of a distant observer. This is not a theoretical concept. TA has been tested and observed in systems like the GPS satellites, where the difference in gravitational potential between Earth and the satellites causes time to run at slightly different rates. For an astronaut near a black hole, the experience would be surreal. From their perspective, time would seem to flow normally as they approach the event horizon. But from the perspective of an observer far away, they would appear to freeze in time, their image becoming increasingly stretched and distorted as they get closer. This is one of the most striking predictions of Einstein's theory of relativity. Time and space are not fixed, they are flexible. They warp and bend under the influence of gravity. But floating, as we have seen, is not just about the extremes of black holes and gravity wells. It is also about understanding the subtle, everyday effects of gravity on our planet and throughout the universe. While space offers a near-perfect vacuum, free from the interference of air resistance and friction, it also offers insights into the way gravity works on both a large and small scale. Take, for example, the Earth's atmosphere. Gravity is the force that keeps our atmosphere in place, preventing it from drifting off into space. But gravity's effect on the atmosphere is also what causes weather patterns, winds, and ocean currents. The planet's rotation, in combination with the uneven distribution of solar energy, creates atmospheric pressure differences, driving the movement of air masses. These movements, in turn, create the winds and weather patterns we experience every day. Floating in space allows us to observe these effects without interference, to see how gravity shapes the behavior of gases and liquids on a global scale, even within our own bodies. Gravity has a profound influence. Our bones, muscles, and circulatory systems are all shaped by the gravitational force that constantly pulls us downward. In microgravity, such as when astronauts spend time aboard the ISS, we see dramatic changes in the human body. Without the constant pull of gravity, bones lose mass, muscles weaken, and fluid redistributes. This is why astronauts must exercise rigorously to maintain their health during long missions in space. Floating in a vacuum is not just about escaping the force of gravity, it's about adjusting to a new environment where gravity's influence is reduced but still present, affecting the body in ways we are only beginning to fully understand. Gravity, as we now know, is a force that transcends simple attraction between objects with mass. It is a force that influences the very structure of spacetime itself, shaping the path of light, bending time, and dictating the movement of planets, stars, and galaxies. But perhaps the most profound lesson floating in space teaches us is that gravity is not just a force, it is a property of space itself. It is what makes space behave the way it does. This realization came slowly to humankind. First, with Newton's law of universal gravitation, and later with Einstein's general theory of relativity. Each of these theories offered a deeper understanding of gravity, revealing its far-reaching effects on both the macroscopic and microscopic scales. But even Einstein's work is just a step toward a more complete understanding of gravity's true nature. As we continue to explore the cosmos, new discoveries about gravity continue to emerge. We've already learned that gravity can stretch light, bend time, and even influence the formation of galaxies. But we still don't fully understand the nature of gravity at the smallest scales. What happens when gravity meets the quantum world? How does it behave when applied to the smallest particles, those governed by the strange rules of quantum mechanics? This is the great question at the frontier of modern physics, the search for a theory of quantum gravity. Physicists are working to reconcile the two great pillars of modern physics: general relativity, which governs the behavior of massive objects, and quantum mechanics, which governs the behavior of subatomic particles. The unification of these two theories remains one of the biggest challenges in science, and a deeper understanding of gravity could hold the key to unlocking the mysteries of the universe. One of the most exciting areas of research in this regard is the study of gravitational waves. These ripples in spacetime, caused by massive objects like black holes or neutron stars colliding, carry information about the fabric of space itself. By studying gravitational waves, scientists hope to gain insights into the behavior of gravity at the quantum level and, perhaps, even discover a new phenomena that could lead to a unified theory of everything. As we move forward, the more we study, The behavior of gravity weather in the quiet vacuum of space, in the extreme environments near black holes, or in the subtle effects it has on our daily lives. The more we realize that gravity is not just a force we must contend with, it is the force that shapes everything. Floating in a vacuum, then, is not just an exercise in weightlessness. It is an invitation to understand the most fundamental truths about the universe. It teaches us about the nature of time, the structure of space, and the intricate dance between mass and energy. It reminds us that, while we may float free from the surface of the earth, we are never truly free from gravity. It is a part of us, woven into the very fabric of our existence. As humanity continues to reach for the stars, gravity will continue to be our constant companion, shaping our path and guiding our exploration of the cosmos. We float not because gravity has disappeared, but because we have learned to move within its embrace. And as we venture deeper into the vast reaches of space, we'll continue to learn from gravity, not as a force to be feared, but as a partner in our cosmic journey. Drifting quietly through the void, one begins to understand that the absence of resistance is not emptiness, is clarity. Every action, every force, every bend in trajectory reveals something hidden when tethered to Earth. Space strips away the noise of friction, of pressure, of atmosphere. And in this exposed silence, gravity becomes not just an invisible pull, but a guiding architecture, the quiet conductor of the cosmic orchestra. As spacecraft glide through the orbital paths determined by mass and curvature, a peculiar truth becomes evident. Gravity does not pull in the way our bodies suggest on Earth. It curves. It's a familiar apple falling from a tree. Once a symbol of gravitational force, is now more accurately understood as the apple following the straightest path in a curved geometry. Earth's mass curves spacetime around it, and the apple, simply following the geometry, appears to fall. In space, this same rule holds, but it becomes beautifully visible when an astronaut lets go of a wrench inside a space station. Both she and the tool continue along their shared orbit. Neither pulls on the other. They move together through bent space. What looks like floating is simply two bodies existing in the same curved frame, tracing its geodesic, the natural trajectory through the warped terrain of spacetime. No engine is needed to sustain their motion. No contact is required to hold them together. Gravity, expressed through curvature, does all the work. This gentle movement is governed by Einstein's field equations, those deeply elegant lines of mathematics that describe how energy and mass warp the cosmos. From these equations, the behavior of stars, planets, comets, and even light itself can be predicted with astonishing accuracy. But the reality they describe is more intuitive than it seems. Gravity is not an external force, it is the geometry of existence. And yet, this cosmic choreography doesn't end with the grand and the vast. Floating in a vacuum allows one to consider the local effects of gravity in new light. Consider two orbiting satellites each the size of a small car. As they circle Earth in similar orbits, their trajectories begin to gently nudge toward one another. Not because they are powered or piloted, not because of any atmospheric disturbance, but because of tidal versus a subtler phase of gravity. Tidal forces arise when gravity's strength differs slightly between two nearby points. On Earth, this gives rise to the tides in our oceans. One bulge toward the moon, one away from it. In space, tidal forces stretch and compress satellites, slowly altering their paths, tugging them toward alignment or disruption around massive bodies like neutron stars. Tidal effects become dangerous. They can tear spacecraft apart or shred stars into luminous spirals of plasma. But in low Earth orbit, they are whispers, delicate shifts, barely noticeable over days and weeks. This sensitivity is part of what makes space research so precise. Instruments like LIGO, built to detect gravitational waves, must isolate themselves from even the tiniest earthly disturbances, passing trucks, tremors, temperature changes. The instruments that observe gravity must float in conceptual vacuums, insulated not only from noise, but from assumption. Because the faintest ripple in spacetime carries history. It's a distant echo of a black hole merger or the collision of neutron stars billions of years ago. Gravity, it seems, doesn't only shape, it remembers. Floating in a vacuum allows the human body to reveal its relationship with gravity. In microgravity, the heart does not need to pump as hard to move blood upward, so it weakens over time. The spine lengthens slightly, uncompressed by weight, leading to back pain in astronauts. Fluids pool in the upper body, creating puffy faces and pressure behind the eyes. The otoliths in the inner ear, tiny stones used to sense up and don't, no longer send consistent signals, leading to disorientation. Every organ, every system has evolved in gravity's embrace. Remove that familiar pull, and the body becomes a study in adaptation. Muscles atrophy without resistance. Bones demineralize. Red blood cell counts change. Even the immune system shifts. Floating is not a neutral state. TIT is a biological stressor that must be studied, understood, counteracted. And yet, it is in these changes that space teaches us something profound. Not just about the human form, but about evolution itself. Every adaptation, every structure, every function of our physiology bears the fingerprint of Earth's gravity. Without it, we change. Slowly, but surely, we become different beings. To float in space is to exist briefly in an alternative physics, a different frame, where familiar assumptions dissolve. Flames behave differently, forming perfect spheres rather than flickering plumes. Fluids do not settle, but cling in balls. Bubbles do not rise. Convection halts. Even the concept of up becomes meaningless. Space offers not just a vacuum, but a mirror, reflecting the gravitational biases we carry without knowing. This altered environment is a laboratory for invention. Technologies designed for spaceflight, like water filtration systems, radiation shielding, and compact nutrition, find their way into life on Earth. But perhaps, more importantly, floating in a vacuum gives us tools to imagine alternate realities. What would human life look like on a planet with twice Earth's gravity, or on a moon with a fraction of it? Could architecture exist without weight? Could medicine evolve without pressure? Already, we simulate these questions on parabolic flights, in centrifuges, in computer models, but nothing compares to the truth of experience, the hours spent floating. Watching a sunrise bend over the curve of the Earth, or witnessing a droplet of water tumble endlessly in place. These moments, these images, remind us that gravity is not just a law. It is a story, a continuous, unfolding narrative about how the universe holds itself together. A tale written in curvature, in acceleration, in orbital decay. A tale that began at the birth of time and continues in every falling leaf, every orbiting moon, every floating astronaut. And while we still search for its final chapter or theory of everything, perhaps we already live within its plot. Floating in space does not suspend gravity. It reveals it. Quietly, insistently, gravity remains not as a force that holds us down, but as the condition that makes motion possible, as the architect of every structure we know. In this way, the vacuum of space is not empty at all. It is full of truth, full of motion. It's full of gravity's whisper. There is something oddly comforting about the idea that in the vastest reaches of nothingness, there still exists an invisible thread of continuity that pulls galaxies into spirals, keeps moons obediently circling, and persuades particles to fall in line. Gravity, silent as breath, stretches across the great void, ignoring distance and time, shaping not just the large, but the small, not just the moving, but the still. Floating in space is not the same as being free from gravity, even at the height of the International Space Station. Gravity is nearly as strong as it is on Earth's surface, about 90% of what we feel on the ground. The sensation of weightlessness comes not from the absence of gravity, but from being in free fall. The station and all within it are falling together, perpetually missing the Earth. This shared fall is what creates the illusion of weightlessness. It's gravity itself that enables astronauts to float. This realization transforms our understanding of motion. On Earth, acceleration and resistance are constant companions, but in orbit, movement continues unbothered unless something interrupts. A push remains a push. A spin continues forever. The vacuum preserves momentum with a kind of reverence. It reveals the truth Newton captured long ago: objects in motion remain in motion unless acted upon by a force. Here, in this frictionless expanse, that law becomes more than theoretical. It becomes visible. Objects tumbling inside a spacecraft behave with a slow elegance, moving as if underwater, but with none of the drag. Their motion is not hindered, only defined by the precise amount of energy imparted. A wrench spun in midair continues to rotate. A droplet of water, nudged from its surface, slowly arcs away, merging with another drop like two silent thoughts. Joining the ballet of inertia and equilibrium plays out with hypnotic grace. This purity of motion allows scientists to study dynamics in a way Earth's clutter would never allow. How particles interact, how fluids behave in microgravity, how combustion behaves without convection. These are more than curiosities. They are pieces of a larger puzzle. In the vacuum, cause and effect become more isolated, more measurable, and in their clarity, new ideas begin to form. One of the most profound is the concept of microgravity's effect on phase changes. On Earth, when water boils, hot fluid rises and cool fluid sinks due to gravity-driven convection. In space, this doesn't happen. Heat does not rise. Instead, temperature distributes by conduction and radiation alone. A boiling bubble doesn't rise, and burst remains suspended, stable, unmoving, like a thought paused mid-formation. Fire behaves differently. A candle flame on Earth is teardrop-shaped because of the upward pull of heated gases. Orbit, it becomes a sphere, a soft, glowing orb that consumes oxygen slowly and evenly from all sides. It lacks the flicker we associate with flames. It has no direction, no base or tip, and it burns with a quiet steadiness that borders on eerie. In such conditions, scientists are able to examine combustion without turbulence, studying the chemistry with a precision impossible on Earth. These insights help design safer fuels, better engines, more efficient burners, but they also offer something more subtle in understanding of how gravity choreographs even the smallest of flames. It makes the flame dance, leap, bend. Without it, the fire meditates. Even biological systems respond differently. The simple act of cell growth is affected by gravity. In a microgravity environment, cells behave as though their spatial awareness has changed. They grow in 3 dimensions instead of forming flat layers. Their gene expressions alter, their signaling shifts. Experiments in orbit allow researchers to study disease processes like cancer and Alzheimer's in new ways by observing how gravity influences cellular architecture. Plants to behave differently. Without gravity to guide their roots downward and stems upward, they must rely on light and moisture alone to orient themselves. Some continue to grow properly, others twist strangely. Studying these patterns teaches us not only how to grow food in space, but also how deeply Earth's gravity has molded the design of life. And yet, despite these adaptations, floating in space carries risks. Without the constant pressure of gravity, bones begin to lose calcium, muscles shrink, balance systems falter. But perhaps the most subtle and haunting change is in the human sense of time. Time seems to stretch in the vacuum, without day and night, without sunrise and sunset. Without the gentle cues gravity provides, like the weight of a footstep or the resistance of lifting a cup, the rhythm of days begins to fade. Astronauts report a dreamlike quality to time. Hours blur, days lose their edges, sleep becomes difficult, wakefulness feels unreal. The human body, it seems, relies on gravity, not just to move, but to know when to rest. Some space travelers describe a kind of psychological buoyancy that emerges, freed from weight, from the sound of footsteps, from the clamor of a busy planet. I begin to feel both deeply detached and curiously connected. The view of Earth from orbit, the famous overview effect, brings with it a sense of unity, of fragility, of perspective. It is as if gravity's absence makes us more aware of what we always carry with us, the need to belong, to hold on, to feel grounded, even when we are not in the vacuum. This paradox is sharpened. Gravity is gone, but not forgotten. Its influence is still everywhere, defining trajectories, shaping orbits, curling light, yet it is no longer felt directly. It becomes background, invisible, but necessary. It's like a song's rhythm. You don't notice until it stops. This background hum is what allows spacecraft to circle planets, what holds comets in their ancient paths, what binds galaxies in slow spirals. Gravity does not need presence to act. It simply exists, a silent geometry drawn across the fabric of spacetime. Floating in a vacuum teaches us not that gravity is weak or absent, but that it is persistent. Even when its pull can't be felt on the skin, it continues to shape everything we see, the stars we observe, the light that bends around them, the path a spacecraft follows. All are whispers of gravity's reach. This understanding is not just theoretical. It influences engineering. Spacecraft must be designed with the knowledge that fuel will behave differently, that systems will vent and pressurize uniquely, that tools will float and rotate without resistance. Every lever, every wire, every sensor must consider what happens when gravity's grip is loosened, and as missions extend further toward Mars, toward deep space. This knowledge becomes survival. How to land without gravity's cue. How to grow food in a greenhouse where water forms globes instead of streams. How to repair systems when bolts float away at a touch. These are not futuristic puzzles. They are practical ones, informed by the simplest fact of all, that we are gravity's creatures. We evolved under its pull. We walk, breathe, digest, and sleep in rhythm with its presence. And when we leave it behind, even briefly, we become not just explorers, but experiments. Floating in a vacuum becomes more than a state of matter. It becomes a state of mind. A place where assumptions dissolve, where motion obeys only the cleanest logic, where time softens, direction vanishes, and the quiet echo of gravity remains, constant and unseen. In this stillness, new questions arise. If gravity bends light, what else might it bend? It shapes time. What does that make of memory? Absence of weight. What defines presence? There are no final answers in space, only trajectories, and every floating object continues. The deeper one drifts into the vacuum of space, the more peculiar gravity becomes. It's no longer just a downward pull or a force that keeps things from floating away. It becomes something woven into the fabric of how reality behaves. In orbit, gravity reveals its subtleties. In deep space, it reveals its mysteries, far from the orbits of planets or the noise of solar radiation. A spacecraft entering interstellar space carries with it more than instruments and ambitions. It carries questions about how the universe is shaped, not just physically, but philosophically. What does it mean to float, not around something, but toward nothing? In these dark reaches, gravity does not disappear. It stretches. It whispers. Even here, many billions of kilometers from Earth, it governs how the spacecraft moves. Speed, its path, even its faint wobble all are expressions of an unseen gravitational landscape. Consider the Voyager probes, launched in the 1970s. They still move, carried not just by their engines, but by the trajectory gravity laid out for them. Their course was plotted using a method called gravity assist, where they passed near planets and used their pull to slingshot faster and farther. It's as though gravity were not just a force, but a kind of planetary current, one that could be surfed if you understood the rules. This technique of using gravity as a slingshot was not merely clever, was necessary. Without the fuel to travel such great distances, the only way forward was to cooperate with gravity, to let it bend the path rather than resist it. These maneuvers changed the way we think about motion in space. They showed that gravity wasn't just something to overcome, was something to harness. The vacuum, so quiet and still, is shaped by these invisible currents. A spacecraft does not simply drift randomly. It follows the contours of gravitational wells, the hills and valleys of mass scattered across space. These aren't visible. There are no signs, but they're there, written into the paths of planets, the timing of comets, the loops of binary stars. The farther one gets from a gravity, well, the slower time moves relative to those still deep inside one. This is a consequence of Einstein's general relativity, that gravity doesn't just affect space, it affects time itself. The stronger the gravitational pull, the slower time passes. This means that an astronaut floating far from any planetary body in deep space would be aging ever so slightly faster than someone on Earth's surface. It's not science fiction, it's measurable. GPS satellites must correct for this every day. Orbiting high above Earth, they experience both special relativity from moving quickly and general relativity from being farther from gravity. Without constant time adjustments, your phone's location could be off by kilometers. In this way, gravity teaches us that time is not universal. It is local. It is curved. This understanding gives a kind of softness to the idea of time. It means that past and future are not rigid pathways. They are shaped by mass and distance. They are fluid, like light itself, which also bends when it passes near something massive. This bending is not a metaphor, it's literal. It's light curves around stars. It bends around galaxies. It creates lenses in space, magnifying objects far behind them. Astronomers use this phenomenon called gravitational lens to study distant galaxies. They look through the warped light created by intervening clusters. In doing so, they not only glimpse ancient light, they map the distribution of gravity. And in that distribution, they find something else. Dark matter. Dark matter is not visible. It does not emit or reflect light, but it has mass. It pulls, it shapes galaxies. Without it, the stars in spiral arms would fly away, flung by centrifugal force. But they don't. They stay. They orbit faster than expected. This unseen mass holds them close. It's floating in a vacuum. Even in the dark, gravity leaves fingerprints. We don't know what dark matter is, but we know what it does, And that knowledge comes from watching how gravity behaves when no visible object is there. It's a bit like watching wind by the way trees bend. You can't see the wind, but you can trace its path. In this way, gravity becomes a tool of detection, not just a force, but a guide. It shows us what cannot be seen. Black holes, for instance, are regions of such intense gravity that not even light can escape. Yet we know they exist because of how they affect nearby stars, how they bend light, how they cause spacetime itself to ripple when they collide. These ripples, gravitational waves, were predicted a century ago, but only recently detected. They move through space like waves through a pond, compressing and stretching distances ever so slightly. The detectors that capture them, LIGO and Virgo, marvels of precision. measuring changes in distance smaller than a proton's width. And yet, these faint signals tell enormous stories of black holes colliding, of neutron stars merging, of cataclysmic events happening billions of light years away. It's all heard, not through light, but through gravity's vibration. It's a kind of cosmic sound. It's a whisper from the fabric of existence itself. What does this mean for someone floating in space? It means that even in silence, there is motion. Even in stillness, there is story. Gravity connects. It transmits, remembers. Floating in a vacuum does not mean floating in emptiness. The space between stars is not blank. It is laced with subtle interactions, with charged particles, with faint radiation, with gravity that stretches from the smallest moon to the largest supercluster. The emptiness is full. Even our solar system is not a closed space. It exists within a region called the heliosphere, where the solar wind pushes back against interstellar space. As you move outward, that pressure drops. At the edge, the boundary shifts. This region, the heliopause, marks where the influence of the sun fades and the galaxy begins. Here, gravity still tugs. But so does radiation, wind, magnetism. The forces become delicate, less predictable, more entwined. A body floating here is suspended between influences. It's no longer pulled primarily by Earth, not yet drawn into another star's domain. It is a region of transitional liminal zone. And in that liminality, gravity is still the constant, the compass, the storyteller. It doesn't demand attention. It doesn't make noise, but it is always there, holding things in relationship, giving orbits their rhythm, giving weight its meaning, and even in its gentlest form, it gives direction. Space teaches us this patience, that motion doesn't need drama, that force can be quiet, that connection is not always visible, and that to float, truly float, is not to be lost, but to be in balance. The astronaut, sleeping in orbit, is not falling. She is gliding. Spacecraft, spinning in deep space, is not alone. It is tracing gravity's lines. The satellite, measuring a distant burst of gravitational waves, is not passive. It is listening to the structure of everything, floating in a vacuum. We learn that gravity does not fade. It only becomes more intricate, more precise, more fundamental, far beyond the inner workings of our familiar solar neighborhood. The role of gravity unfolds in unexpected ways, complex, subtle, yet unwavering. While on Earth, gravity feels like a downward pull. In the vacuum of space, it becomes a gentle sculptor, defining not just where things fall, but how everything exists, flows, and evolves in the quiet depths beyond Neptune, far past the Kuiper belt. Scientists speak of the Oort cloud, a theoretical shell of icy objects surrounding the sun like a vast fog. No one has ever seen it directly. It lies tens of thousands of astronomical units away, a faint halo of dormant comets. But gravity binds it, not tightly, not urgently, but persistently. Every so often, one of its ancient bodies drifts too close to a gravitational tug, perhaps from a passing star, or the combined influence of distant planet sand is nudged inward. 8,000 of years later, it might grace Earth's sky as a long-period comet. This invisible interaction is one of gravity's quietest expressions. The Oort cloud doesn't need to be close to feel the pull. It is a distant member of the sun's family, bound not by heat or light, but by a whisper of mass reaching across unfathomable distance. In space, the farther you go, the more you realize that being far away doesn't mean being disconnected. And it's not just our solar system. The galaxy is filled with interactions like these. Rogue planets, drifting between stars without a home, still feel gravity's hand, though not orbiting a sun. Their paths are shaped by the mass of the Milky Way. Their journeys are long and dark, but not without guidance. The same applies to dust, gas, and fragments of matter. All these seemingly insignificant particles float, not randomly, but along the invisible currents that gravity sculpts across galactic space. Spiral arms of galaxies, those sweeping, elegant structures, solid formations. Their density waves, regions where gravity compresses gas, triggering new generations of stars. Star formation itself is an act of gravitational patience. A cloud of hydrogen, gas cold, diffuse, and dim begins to collapse under its own weight. Slowly, the atoms draw together. Over thousands, or even millions of years, they pull tighter, growing denser, warmer, more reactive. Eventually, fusion ignites in the core, and a star is born. But even in this birth, gravity is the midwife and the protector. It balances the outward pressure of fusion with the inward pull of mass. Should the balance shift, stars expand, contract, or die. Supernova, neutron stars, and black holes are different endpoints of that gravitational balancing act, floating in a vacuum. Far from this process, a small observer might be tempted to think gravity is absent, but in fact, it is everywhere, layered, braided into the very architecture of the cosmos. Every object, no matter how faint, how cold, or how still, has mass. And where there is mass, there is curvature of space and time. This curvature isn't just theoretical, it can be observed. One of the more poetic confirmations of general relativity came during a total solar eclipse in 1919. Scientists measured the positions of stars near the sun's edge. Their light appeared shifted, bent, not because the stars had moved, but because their light had followed a curved path through space. The sun's mass had warped the space-time around it, and gravity had revealed itself not as a pull, but as a lens. The idea that gravity can bend light and, by extension, affect what we see has become central to astrophysics. Observations of distant galaxies are constantly filtered through this cosmic distortion. What we observe is not always where the object truly is. Light's path has been altered en route. This doesn't make the universe less reliable. Mincing makes it more nuanced. The vacuum, it turns out, is not a vacuum in the traditional sense. It's not empty. It has shape. It has behavior. It can ripple, flex, and bend. And because of that, even in places where there are no stars, no planets, and no dust, space remains dynamic. Gravity persists, silent but certain, in microgravity environments like those aboard the International Space Station. This reality becomes intimately human. Astronauts adapt to a world where up and down no longer apply, where motion never stops unless intentionally canceled. Their muscles weaken, their fluids redistribute, their sense of orientation shifts, but gravity hasn't gone. It simply changed its relationship to them. They are still orbiting Earth, still falling, but sideways, with a precision and purpose. The orbit isn't a rejection of gravity. It's a dance with it. The station's speed over 28,000 kilometers per hour keeps it suspended in a state of perpetual fall. It moves fast enough that the curve of its descent matches the curve of the Earth. In doing so, it floats but never escapes. This balance is not coincidental. It is gravitational choreography rehearsed by mathematics, played out in silence. Floating in this condition, astronauts experience the world in a profoundly different way. Objects don't fall, they drift. Movement requires subtlety. A touch on a surface sends the entire body backward. Sneeze is an impulse. A tool left unattended won't drop it, will wander. And yet, despite these differences, gravity remains their reference, their anchor. Without it, their return to Earth would be impossible. It is gravity that guides the re-entry capsule that pulls the spacecraft back through layers of atmosphere, slows it with friction, it's gritty, and welcomes it home with the unyielding firmness of ground. This journey from freefall to return is echoed on a larger scale by moons around planets, planets around stars, stars around galaxies. Orbits are the rule, not the exception. And when they are disturbed, it is gravity that mediates the change. Collisions, mergers, tidal disruptions. These are not chaos. They are gravity expressing itself in motion. One of the most beautiful examples of this is the dance of galaxy pairs. Over billions of years, two galaxies may drift toward one another. Their outer stars begin to interact, drawn slightly off course. Tails of stars and gas stretch between them. Spirals deform. T's nuclei merge. Eventually, a new, single galaxy forms larger, brighter, shaped. This cosmic merging is not violent in the way we often imagine. Stars rarely collide. The space between them is too vast. Instead, their paths shift, their orbits adjust, their relationships change, and gravity conducts it all, not as a destructive force, but as a reassembler. Floating near such an event, if one could do so safely, would not feel like tumbling into wreckage. It would feel like drifting through the slow rearrangement of structure, like watching the ocean reshape a coastline not overnight, but over eons. Even at the largest scales, gravity retains this character. It does not impose, it invites. It enables relationships. It defines systems. From particles clumping into dust, to dust forming planets, to planets circling stars, to stars weaving galaxies. Gravity does not build by brute force. It builds by attraction. That simple idea that everything pulls on everything remains one of the most profound truths we know. And it holds, even now, as you listen, perhaps resting, perhaps imagining that quiet vacuum beyond the stars. Somewhere in that darkness, an object floats empowered, unnoticed. It may be a speck of comet dust. It may be a derelict probe. It may be a wandering rock from a distant system. It doesn't move aimlessly. It traces a path, a curve, a response to all the mass around it, whether near or far. It is never truly alone, because gravity, however faint, is always reaching out in the infinite stillness of deep space, where sound cannot travel, and where light may take thousands or even millions of years to reach a destination. Gravity is the language of connection. It whispers across blackness with patience and without interruption, even where there appears to be emptiness, even when nothing visibly moves or collides. Space is humming with its own kind of communicational pool between objects that may never meet. This notion becomes even more fascinating when we turn our gaze beyond galaxies to the structure of the universe itself. When astronomers attempt to map the cosmos on the largest scales, they don't see a random scattering of galaxies. Instead, they see filaments, vast, thread-like clusters of matter forming a kind of web across the observable universe. Between these filaments lie enormous voids, cold and dark and seemingly barren. This cosmic web is thought to be the result of gravity working over unimaginable timescales. After the Big Bang, matter was not evenly distributed. Some regions had slightly more mass than others. Gravity, with infinite patience, has turned these tiny differences into patterned stints, knots of galaxy clusters, connected by strands of galaxies and gas, all shaped by gravitational attraction. What's even more striking is that this structure isn't just about matter we can see. In fact, most of the gravitational influence in the universe comes from something invisible, dark matter. This mysterious form of matter does not emit, reflect, or absorb light, but it has mersand. Therefore, gravity is believed to form halos around galaxies to give them their shape and hold them together. Without dark matter, galaxies as we know them might not even exist. They would spin apart, unable to hold themselves together by the gravity of their visible mass alone. This unseen scaffold helps form galaxies, guide stars, and shape the universe. Floating through a vacuum, then, doesn't mean floating freely. It means floating within a structure that's as real as anything else, even if we cannot see it directly. On Earth, we experience gravity as something reliable. Drop a stone, and it falls, spill water, and it flows downward. These are immediate effects. In space, the behavior of gravity reveals itself slowly and across distances. There's no surface to land on. Instead, everything is always falling, always curving, always responding to the presence of massive N if it's light years away. This principle, that gravity acts not through force fields, but through the curvature of spacetime, was one of the major contributions of Einstein's theory of general relativity. According to this theory, mass tells space how to curve, and curved space tells mass how to move. To imagine this, physicists often use the analogy of a trampoline. A heavy ball placed in the center of a stretched sheet will create a dent. If you roll a smaller ball nearby, it will spiral inward, not because the larger ball pulls on it directly, but because the sheet is deformed. The smaller ball follows the curvature. Now imagine that sheet in 4 dimensions, representing not just space, but time as well. Wherever there is mass, that fabric bends, and everything else, from light to planets to stardust, moves along those curves. This reshapes how we think about movement in space. Objects in orbit aren't being tugged by invisible strings. They're simply following the shortest possible path, what physicists call a geodesic through curved spacetime. The elegance of this idea is profound. Motion is no longer imposed by external force, but guided by the shape of the environment itself. And this guidance is everywhere. Even photons, particles of light, which are massless, must follow the curvature of space-time. They pass near massive objects. Their path bends. This effect, called gravitational lensing, allows us to detect mass that is otherwise invisible, such as black holes or clusters of dark matter. In this way, light becomes a messenger, not just of what it encounters, but of what it passes by. There are even moments when the fabric of space-time ripples. It's when 2 black holes collide. The violent merger sends waves through space-time itself. These gravitational waves, first directly detected in 2015 by the LIGO Observatory, are infinitesimal in amplitude, yet massive in meaning. They are confirmation that the vacuum is not inert, that space can move, respond, and carry information. These waves travel at the speed of light and are not absorbed or scattered like sound or light. This makes them pristine carriers of information from the farthest reaches of space. Gravitational wave felt on Earth might have originated from an event that happened over 1 billion years ago. It carries with it the memory of motion, encoded, not in particles, but in the very stretching and squeezing of space, floating in a vacuum. Then, is not like floating in water or drifting through air. It is more like resting on an invisible stage that bends and flexes in response to every performer. The vastness of space is not a void, is a medium through which gravity speaks. And yet, with all this complexity, gravity remains consistent. It always attracts. It never pushes. It operates with perfect indifference to the type of matter or the reason for movement. Whether it's a feather, a spacecraft, or a black hole, gravity treats them the same. It pulls on mass, and it curves the paths of light. This universality is part of what makes gravity so reliable and so mysterious. It's the weakest of the 4 fundamental forces, billions of times weaker than electromagnetism, yet it is the one that dominates the cosmos. It cannot be blocked or shielded. It operates over infinite distances. And it shapes the grandest structures in existence. Even in our most advanced experiments, gravity's mystery remains. Quantum mechanics and general relativity, the 2 pillars of modern physics, describe nature with extraordinary accuracy, but they do not agree when it comes to gravity at the smallest scales. There is no complete theory of quantum gravity. No unified explanation that joins the probabilistic world of particles with the smooth curves of space-time floating in the vacuum. Then is not just an experience of wonder, but of mystery, a gentle reminder that what we know is vast but not complete, that every satellite, every telescope, every drifting particle is part of an experiment still unfolding. Back aboard the International Space Station, astronauts conducting every day tasks do so with this knowledge surrounding them as they float through modules and fix instruments. They are not just performing science. They are living science. Their very bodies experience changes, muscle loss, fluid shifts, altered circadian rhythms, all because they are temporarily suspended in microgravity. These changes are not just physical, they are perceptual. Without gravity to orient them, their brains must recalibrate, Up and down become choices, not absolutes. A coffee pouch doesn't sit on a table, it hovers, Tear doesn't fall, it clings to the skin, A whisper doesn't carry, but a gesture is seen from across the cabin. And yet, when it is time to return, the descent is guided by gravity once again. The spacecraft reorients, the thrusters adjust its trajectory, and the capsule re-enters Earth's atmosphere, drawn back by the same invisible pull that launched it away. The astronauts land, and with trembling legs, they remember the weight of home. As the vacuum stretches on, silent and black, beyond the grasp of air or warmth, gravity remains the one presence that never entirely disappears. Even where it feels like nothing exists, there is motion. Not random motion, not chaos, but curved, weighted, meaningful drift, shaped by an invisible order we only began to understand in the last century. In this final descent through thought, we trace how this most subtle force governs more than planets and stars. It governs perception, time, and what it means to move at all, from the earliest myths of falling skies to Newton's falling apple. Gravity has captured the imagination of thinkers. It took centuries of careful, deliberate observation before we began to describe it precisely. But long before we named it, we experienced it. Every culture, every child, every falling leaf knows its direction, knows its silence, and it's that silence, that calm pull which makes gravity feel less like a force and more like the background hum of existence, even at a quantum level. Where most things lose definition, gravity lingers as an anomaly. Scientists working with particles and fields have managed to unify the other three fundamental forces: electromagnetism, the strong force, and the weak force. But gravity doesn't play by those rules. It resists. It defies simplification. Some think gravity may not be a force at all, but an emergent property, result of something deeper still, perhaps related to the distribution of information across space and time. The idea that gravity could arise from entropic principles or quantum entanglement would change everything. In this view, gravity is not fundamental, but woven from the threads of other interactions we've yet to fully map. For now, though, relativity remains the best compass we have. It tells us how mass and energy shape the geometry of space-time. It tells us why GPS satellites must adjust their clocks to remain accurate, because time runs differently at altitude than it does at the Earth's surface. It tells us how black holes form and how gravitational waves travel. It tells us that when we float in space, we are not weightless because gravity is absent. We are weightless because we are in free fall, falling along a curve of space-time, too vast to see. But what of consciousness itself? Here, too, gravity has a role. Neuroscientists have long known that orientation and balance are tied to the vestibular system, which relies on gravity. Without it, astronauts experience disorientation, nausea, and changes in perception. The sense of up and down, so constant on Earth, becomes irrelevant. In space, astronauts must reprogram their intuition. Forward becomes relative. Objects do not rest, they float. And with that shift, the brain rewires itself. It's here that gravity becomes more than a physical interaction. It becomes psychological, emotional, even symbolic. Gravity grounds us literally and metaphorically. When we lose that grounding, our thoughts change, our awareness of self changes. On Earth, this effect can be subtle. A change in altitude affects mood. A descent into water alters perception. But in orbit, the change is immediate. The human body, evolved over millennia in Earth's gravitational field, must suddenly adjust to an entirely different rhythm. Muscles atrophy, bones weaken. The heart no longer fights against gravity to pump blood upward. The body distributes fluids differently. Even the shape of the eyeball can change. And when astronauts return to Earth, many speak of a profound shift in worldview, the so-called overview effect. It is not just seeing Earth from space, but seeing it suspended in blackness, held not by a pedestal, but by gravity. No borders, no noise, just one blue orb, moving silently through the cosmos. That experience, they say, changes them. It resets their sense of scale. It alters their understanding of conflict, of unity, of life itself. Gravity, then, is not only the force that binds stars and galaxies, it is the force that creates context. Without it, there is no horizon, no reference, no way to say here or there. It is the universal tether in the deepest parts of space, where gravity reigns in its most extreme form. We find black holes. These are not objects, strictly speaking, but regions where gravity has collapsed space so completely that nothing, not even light, can escape. Yet, even black holes are not absolute voids. They spin, they radiate, they can collide and merge, sending ripples through space-time itself. At the edge of a black hole lies the event horizon, the boundary beyond which no signal can return. For an outside observer, time seems to stop at this threshold. Falling object slows, redshifts, and fades. But from the object's own perspective, it crosses the horizon without fanfare, continuing inward into regions where the known laws of physics begin to break down. What happens inside a black hole remains a mystery. Theories abound. Some speak of singularities, others of quantum foam, others still of tunnels to other regions of space-time. But what all agree on is this: gravity, under extreme conditions, is a portal to the unknown. It is possible, though speculative, that gravity could be the key to unifying physics. Some propose gravitons, hypothetical particles that carry the gravitational force akin to photons in electromagnetism. Others explore string theory, which imagines gravity as a vibration of tiny one-dimensional strings, existing in higher dimensions. And then there are theories that question whether gravity is even constant across time. Could the gravitational constant have been slightly different in the early universe? Might it vary under certain conditions? These are not idle thoughts, but real questions being explored in labs and observatories back here on Earth. Gravity shapes everything from architecture to agriculture, the way rivers flow, the way mountains erode, the way seeds grow downward, roots first, responding to a pull they cannot see. Even the posture of the human body, the tension in tendons, the compression of joints, all are choreographed by gravity. Artists have long tried to depict weightlessness, dancers leaping, birds soaring, balloons drifting, but they do so against the contrast of gravity. The joy of flight exists only because of the presence of a pull. A release from weight only makes sense when weight is the norm. That's why, in stories and dreams, floating often symbolizes freedom, escape. But even in fiction, something brings the character back, a return, a landing, because gravity is not the villain. It is the invisible companion. In the end, floating in a vacuum is not an escape from gravity. It is a deeper experience of it. An encounter with its subtlety, its reach, and its quiet insistence. It is a moment of awe, a reminder that motion, rest, and existence itself are all shaped by a force we do not fully understand, but always feel. Whether in orbit, in free fall, or in thought, gravity remains, always pulling, always holding, always shaping the fabric of everything we are.